Oh, hi. Hold on. Okay, hi. So what I want to do now is just give the core algorithm for bootstrap sampling using R and justify it slightly and do an example from our data that we have. So let's see. So I should screen share. So let's share the screen. Okay, so here we are. So going to probably should have set this up first, right? It's okay. Work. And now, okay. So let's do the patient satisfaction one, since that's the one I have ready to go. So read table, patient satisfaction, header. Okay, so okay, remember this. So we like to regress age satisfaction, say on age. Okay, so let's just see what we get if we just do, say, mod original. Satisfaction. Age and PS, right? So summary. Okay, so what I wanted to show you was, here we have the, this is B1, right? This is B1 right here. And here's the standard error for B1. Okay, so this is, in other words, this is S of B1, and I can get a confidence interval then, right? Out of this. So, yeah. So, right? So, okay, so sorry, I got distracted thinking about something. So, so what we like to do is, for nonlinear regression, we don't have all the theory about the model carrying through for the distribution of the estimated parameters. So, in other words, I don't know my G is normally distributed, the estimates for gamma. What we'd like to do is have other ways to support this output here, okay? Because the output from the analogous command for nonlinear models, it's called NLS, nonlinear least squares, is makes assumptions based on the approximation. So it's good to have supporting data to suggest that that those estimates are correct. So another approach completely, which doesn't depend on any of these assumptions for the models, is to use a technique called bootstrapping. So what this is in short, because this is more just about giving you the algorithm in R, and I will put the this little algorithm in Moodle too. The idea is, okay, so say here I have, if we look at the data here, I have 46 rows, right? And this comes from a bigger population, but the idea is I sort of consider this to be the whole population. I consider this to be the entire population in the sense that now I want to resample from this with replacement. And if I sort of look at this as the whole population, as a discrete distribution where each row has equal weight, then I can think if I resample with replacement, then in a sense, I've taken a sample from something with a distribution like that, something with a discrete distribution like that. So this is the approach. And why not assume that this carries all the information about the entire population? It's not ridiculous. Maybe in some cases it might be, but in general, not. So it's the data we have, and we may be willing to do that. So this is the idea. So I think, okay, I have 46 here, but I'm thinking of it as the whole population. So in other words, if I had 46,000, say, elements in my population, I would think of it as roughly 1,000 each of these rows. And then so I'm grabbing, say, a resample from that 46,000 or something, or I'm grabbing a sample that's maybe not a resample from that 46,000, and I'm going to take statistics from that. Okay, so that's the idea. So I'm going to resample from it several times, and the resamples will be samples. So here's the approach. So should I write it down? So here's the approach. So so Bootstrap. I'm just going to type it right here. So Bootstrap. Okay, so step one, resample from I hope I'm recording. I think I'm recording. Resample from the data set, right? From PS. Okay, with replacement. So this gives me what I want. Otherwise, it would skew, right? If I didn't replace or something, it would just be like repeating this information or skewing it. Okay, so that's the first thing. So I resample from PS with replacement. Then, what do we do next? Compute a or several from the resample. So an example might be like B1, okay? Save the statistic and resample and repeat. Okay, 4. Say after, say M resamples, we have a sample of the statistic, size M, and we can make statements about the statistic now. We can say this is the mean of the statistic, this is a confidence interval for the statistic, standard deviation, and we can estimate those anyway. And so we have another insight, another look at how to estimate the mean and standard deviation of B1, and even see the shape of it by looking at the histogram of the statistic, okay? So let's write that down. So statistic, because if we do a lot of these, okay, statistic has info on mean, SD, and even distribution shape of B1. Okay, so we can find confidence intervals, so all of that. So in what follows, I'm not going to do everything, but I want to do to show you the core algorithm to how to, basically I want to show you to how to do part 1, part 2 here, and part 3, save it in a vector, and then maybe one thing about the statistic. The rest you'll have to do, and you'll have to modify this for the problem you have. And if you're trying to use, say, a nonlinear versus a linear. Okay, so what I'm going to do is just put in the code I wrote ahead of time, and then we'll talk through it, and then we'll talk through it, and then we'll look at the data and make some inferences, or at least examine the data. Okay, so this is for the patient satisfaction. I loaded it in already, hopefully. Yeah, okay, so I said I wanted to do, okay, so here's the code. So from here down, there's a big for loop, and that's why you get these pluses here. I haven't closed the for loop yet. So, okay, so let's read it line by line. So it starts, initialize, set aside some memory. It makes it simpler for where you're gonna store your statistic. You could have several in here if you want. You can actually store everything if you want, but you don't really need everything. Say we just want to understand if our estimate for B1 is correct. And keep in mind, for linear regression, this should not be if, well, actually, this is a good way. Actually, this is another diagnostic for normality of the error term. So it applies to linear regression too. But for nonlinear regression, certainly, when you're making all those approximations and saying, you know, it's nice to have some backup here. So this is another way to look at it to see if maybe it appears to be normally distributed. So I have B1 star, and I'm calling it star because it's the bootstrap B1. Okay, so I could have called it B1 boot or something. And so I make a vector size 100, initialize it to 0. And now for k equals 1 to 100, I'm in this loop here, and I'm going to do the following. So I take a vector of size 46, and I set it to each element of that. So for each of the 46 numbers, I pick a number between 1 and 46 with replacement. In other words, there's nothing. RUNIF will just give you, you know, every time in that vector, it's going to give you a random number between 1 and 46. So new set, be fun to look at it, but I can't right yet. But it will just be a bunch of numbers. Now it'll have some repeats in it. It will leave some out. The idea is I'm sampling randomly from the original data set, which I now consider to be 100% representative of the population. Okay, so that's that. So so I now have a vector that, you know, this could be, new set could be like 3, 7, 12, 40, 42, 33, 33, you know, 12, you know, it's gonna have repeat. Okay, so now I set PSB, that's my patient satisfaction boot. Okay, and I'm gonna throw this out every time. I'm gonna compute B1 for this resample, and then I'm going to throw the PSB in the garbage and just reuse it. Seems simple enough, right? So I set PSB equal to PS. This identifies row new set 1. Okay, row new set 1. And by calling PSB here, to equal this by default is 1. So I could have put that in. I could have wrote PSB. Actually, then though, I would have needed to initialize it, I think. So I think this is the right way to do it. It will initialize PSB and set the first element in it equal to new set 1. Okay? So I don't know what row from PS that is, but that's now the first row of PSB. And now, for I, the rest of new set 2 to 46, I want to bind those to PSD. So I go through and set PSB equal to the old PSB, but now I bind this, see here, this whole thing, PS new set I to there. So this is the, whatever new set, whatever that random number is there, as I goes from 2 to 46, that's the one I take from PS and append it to PSB. There are other commands to do this, but I stick with, my learning is growing more slowly, so I stick with the ones I trust and stuff like that. But I'm sure you could find more clever ways. Okay, so now we're there. We've loaded up our bootstrap sample, PSB. And now I compute B1. So I just do LM. Okay, if you're in nonlinear space, you're going to do NLS or another nonlinear modeling command. So I want to model satisfaction versus age as above, and I do that over and over again. I can write it here and I'll just overwrite it every time because I'm going to throw away the whole model, except I'm taking my fruit out, my B1, right? Remember, R uses 1-based indices, so starts at 1. So coefficients 1 is actually B0. Coefficients 2 is B1. Okay, so if I close the bracket here and return, it should run. Looks good. Should I put the music back on, or it's okay, right? All right. So why is it taking so long? Okay, didn't take too long. So let's just see what the last new set was. So you see this is just randomly jumbling these up, and do you see any repeats? Yeah, 7. 4 7s. Wow. Okay. 2 43s. Okay. Anyway, so each new set has done this 100 times, right? And then each one generates a new PSB. We could look at PSB too while we're here. PSB. Now, look, what's going on here? We only went to 46. So what's this, 151? Oh no, it's a mistake. Well, what these are is 15 came twice, so it added a 1 because it uses the ID field too here, and it didn't want to. So the ID field's created when you read table, and it doesn't want to have duplicates, right? So where's 431? You see here's 43. So when you get to here and see 43 again, it adds a 1. I have a 121. This is interesting. It tells you how many duplicates you have too. They thought of it a lot, didn't they, when they designed this? Okay. All right. So what do we really want? What do we really want? We want B1 star, right? So B1 star. There it is. So there's all the estimates for B1. Okay. So remember up here, it was, we still have it. It was minus 1.52. And if I come down here, I get, roughly around there. Looks pretty close, right? So we can look things like mean, B1 star. These are quick things to do. Pretty close, right? In fact, what's the error is, the standard error. The standard error, it claims, is 0.1799. So 0.18, 0.18, 0.152, 1.52, I mean negative 1.52. So, yeah. So look, that's in one standard error, certainly, right? 0.18, 0.18, was it? Not quite then, 0.18. Yeah, no, it is. Okay. Sorry, it's the negative. So certainly, right? This is 0.04 away from the mean. Okay. So this is the idea. I could look at a histogram, B1 star, and check for normality. See, it's negative. So 1.4, the mean should be around here, right? Right around here. Looks good. Looks pretty normal. This is some strange outlier over here, but looks good. Okay, so when you're doing NLS, when you're doing nonlinear analysis, nothing's really different about the bootstrapping. Nothing changes, right? Nothing changes. You still need to use, I suppose, their tools to get your estimates, but then you can check and verify that the estimates appear to be normally distributed and that they appear to give you the same mean and standard deviation as your test did. Your test doesn't use this to do it. It uses theory about central limit theorem, and the strong law of large numbers is used here. And in the test, you're using, well, maybe you're using the same thing. You're using these approximations because it's called large sample theory. So I guess the two theories are both there in both, but they're coming at you from different directions, certainly. Okay, so this is to be thought of as a different different lens at the same how should we say it, at the same estimates, right? At the same estimator or the same estimates. So it's a different lens at it. Okay, look, I wanted to show you the algorithm mainly, and I'll put that little algorithm up in Moodle. And what you should do is, when you have a problem where you need to bootstrap, you take that and you look, and basically that will give you the the logic of it and the how to write things and that. But you will probably have to edit it for different data sets, possibly a different modeling command like NLS for nonlinear least squares, and maybe other things too, the numbers, the number of samples, other things like that. If you want to find a confidence intervals now, those are things you're going to have to look at, and part of it is I want you to look at it. So, okay, well, I hope this helps. I have one more video coming on how to use R to use the NLS command to do nonlinear modeling, and I think that's it. Okay, thanks very much. I hope I can now stop sharing and